What's up guys, we are Get Planked, and today we're going to explain to you how we got our project to work despite a global pandemic.
Exercise is one of the key points to a healthy lifestyle, as there are many positive health benefits. However, if exercising is done incorrectly and with poor form, your body is at risk of getting injured. The idea behind the workout monitoring system is to develop a system that provides feedback on the user's form for the push-up and plank exercise. Both of these exercises can result in injury if not done correctly. To combat this, the workout monitoring system will be used to assist the user in striving for perfect form. The workout monitoring system will result in the user having more confidence, better results, and most importantly, injury prevention.
We'd initially planned to use flex sensors and a webcam for our system to determine that the user's body position is correct. However, we modified our VI to mimic the use of these devices. For flex sensors, as the sensor is bent, the resistance in the device changes. When in a voltage divider circuit configuration, this varying resistance results in a detectable amount of output voltage that corresponds to a certain amount of bending. The flex sensor in our system was meant to determine if the user's back was flat or not. A flat back means the user is in the correct form for a given exercise. In the case of our modified VI, we added a dial that mimics the ability of a person bending their back. Deflection varies linearly with resistance in flex resistors, and as a result, an equation was developed to relate resistance to this hypothetical change in deflection. This hypothetical resistance is then subbed into the equation for a basic voltage divider circuit with a fixed reference voltage of 5 volts and a fixed resistance of 10 kiloohms in order to find a hypothetical output voltage. An output voltage of 2.5 volts serves as a reference for a flat back, given that this output voltage corresponds to a flex sensor with zero deflection. That output voltage would then be compared against voltages corresponding to certain amounts of deflection to determine if the user's back is not too bent. 0 to 10 degrees of deflection was set to be perfect back position. 10 to 30 degrees of deflection was deemed to be adequate back position, while 30 degrees and above was deemed to be incorrect form. These values were arbitrarily chosen given that data from actual testing with flex sensors was required to determine these limits. Webcams, on the other hand, are used to obtain image data in the form of a live video stream to be further processed. For our project, image data from a webcam would have been compared against a still calibration image of a user in proper form to determine if the user's arms and body position is in the correct position for a given exercise. In the case of our VI, still images are manually selected for, and a test image will be compared against a calibration image for various exercises rather than a live video feed.
VI is no longer using live sensors. We have adapted it, and now it has two parts that represent the two sensors we would have been using. The first part would have been using a flex resistor to measure the back deflection of somebody. And as someone's back has bigger deflection, the resistance of the resistor increases and less voltage will be running through, and this would determine how bad someone's back position is when they're planking or doing a push-up. Now, we can't do that anymore, so we've instead made a dial that determines what back angle that somebody would have, whether it be a negative or positive angle, which means someone's back would either be too concave or too convex. And now, with this dial, we have input it to the formula for a voltage divider circuit, and we know which voltage would be running through that circuit, determining using a reference voltage of 5 volts and assuming nominal resistance of 10 kiloohms. Since the signal from the dial, which was a back angle, has now completely been converted into a voltage signal, it must be multiplied by 100 so that we have 3 usable digits above a decimal place. As the next point, it goes into a case structure. And we use these different ranges in the case structure to determine if the back angle is perfect, acceptable, or unfit. And 3 Boolean LEDs are hooked up to these 3 different case structure variants, and that's how it's determined if the user's back is fit or not. Now for the second part of our VI, this originally would have used a webcam to determine if someone's back was bent or straight when planking or push-upping, if their elbows were not bent or too bent, and so forth. But now we're using still images as test cases with one reference image and one image which is either unfit or perfect. Now, the way this works now is there's a PNG image, two file path directories to determine the reference image and the other image, and then they are both converted into arrays using a convolution function, and then the data type is then turned into U8 to a double data type, or into a 2D array essentially. After both PNG images have been convoluted and then transformed into 2D arrays of doubles, they are subtracted from each other, leaving one array. And then, using the for loops and the add array elements function, the rows are added in the top for loop, and in the bottom the array is transposed so that the columns are added. And then we sum both of these values again to get one single double number to determine how many pixels or how many pixel values are different in the two different images. This difference in pixels value is then measured up against a 0 value, and if it equals 0, then the back image is perfect, but if it doesn't equal 0, then the back is not straight and the Boolean light will not turn on, and this will be a fail.
During our work, our group faced some limitations and errors, much like every other group. One of the limitations that our group faced was with the flex resistors and how they measured. We used one flex resistor, and that couldn't measure direction, but it would measure magnitude and how much the person bended. Another one was our image processing. We actually had to use a tripod to ensure that the background of the image remained constant. We did this because we had to compare pixels, and we wanted to make sure that the pixels in the background weren't changing. Another thing we were limited by was the ability to prototype in real life. We had to do this project virtually, so we weren't able to build a system that we could physically adapt to and work with. We had to adjust things virtually, and we did this by adjusting image files. We're also limited by our budget set up in the project outline, and we could only afford to use one flex sensor. This meant we couldn't measure in one direction, but this is why we brought image processing into our system. We had to bring this project to you virtually because of a pandemic going on, so the group had to work online using resources found on the web. We weren't able to work with each other in person or build the system as a real-world project.
Alright guys, so for potential applications, this is going to be mostly in the gym and stuff like that. So for our project, we decided to do planks and push-ups just because that was the easiest to have consistency with in testing and taking the pictures and stuff like that. But in terms of a real-world application, this could honestly be used in pretty much every workout, mostly because you're doing the same motion repetitively and you want to be doing that correctly. So stuff like pull-ups, bench pressing, curls, stuff like that, where your arms and legs and back have to be moving a certain way, the same way every time. Not only for like making sure you don't hurt yourself, but also being efficient in terms of your time and energy for the greatest return on investment, if you will. Outside of the gym, there are a couple different things like assembly line stuff, specifically like things like welding, where you have to be doing the exact same motion every time. That way all the pieces come out the same. But as of right now, with this virus going around, anything that could help us work out better and more efficient, since we have so much more time on our hands and we're not necessarily being active outside the house, is probably beneficial for us all. Alright guys, that's all we got for you today. Our group had a great time building this VI for the project. We would have liked to have built this in real life, as it's a pretty cool idea, and honestly with all of us being home and stuck at home like this, we're all working out hopefully a little bit more than usual, and so having something like this in real life would probably be pretty beneficial to make sure we're spending our time wisely doing these workouts and like actually getting something out of it. But you know, what are you gonna do with us? You know, we're trying to get the normalcy back with the Lassonde logo like we have in the previous video, but we're doing the best we can. And I want to give a big shout out to all the profs and TAs that somehow made this project work despite not being able to be there in person. So big shout out to you guys. And hopefully we'll see you guys all back in September, and we'll all be healthy and happy and washing our hands more often and good to go. See you guys next time.